Okay, so the review for the practice test, number one, they give you this equation. Y is the number of customers in the coffee shop for X hours that they've been open. So first thing you're going to want to do is graph it and make sure you're watching your window here. I'll give you the grid so you know what to use for your X min and X max. And the graph should look like this. Just plot a few of the points from the table for part A. Okay, part B, we should be noticing two kind of relative peaks or busy times during the day. So it looks like as soon as they open up, looks like kind of a busy peak there. So there's like a maximum here, and then it looks like another rush comes in maybe around here sometime. So to determine the hour in which those occurred, we would need to use the calculator and find the maximums here. Okay, I don't really want just like an approximate, like around 0 or something. Use your calculator. So let's graph the equation. I have that in here in my y equals already. Get rid of this ink here. Okay, so I have a bunch of different equations, and the only one highlighted right now, this is the one from number 1 in y1, and I think I preset the window to match. So we can kind of see that there's a maximum again around here and around here. So we would just use the calculator to find the maximum. So let's find that one on the right there. If I go second, calculate, and find a maximum, and you just need to tell it again where to look, give it some boundaries. So that would be a good left boundary, and then a little bit to the right would be, just to be safe, somewhere like that maybe. Oops, that was a little far, but that's good enough. And then guess, just press enter one more time, and you'll be able to see the maximum happen about 10.3, 10.4 hours after opening. And during that time, it was around 111, 112 customers in the store. Okay, and the other one, it turns out, would actually be just the y-intercept. So you could tell from the equation that the y-intercept was just the constant term in there. So I'd go with the 144 at 0 hours, and then the other one that we just showed over here. Okay, part C, write and solve an inequality to determine during which hours the shop would expect more than 100 customers. So basically, I'm not going to rewrite the whole long equation, but the whole equation is basically y, and we want to know when that will be more than 100. So that's the inequality we want to solve. And problems like this with the really messy decimals and everything, let's just use our calculator. But basically what it's going to boil down to, here's the line y equals 100. Okay, so we are asking ourselves, during which x values is the pink graph above the 100? So we're going to have to find some intersections here. And it looks like from when it started to about there, so we'll find that x value. And then it picks up again here to about here. So in between those green dots, okay, if this was like interval 1, that would be above. Interval 2 would actually be a no for this problem because the graph is below the red line. And then interval 3 would work again. So using your calculator, you can get those intersections pretty easily. So the way I did it was I had the original equation in there already. I put in a different y equals. I put in the 100, which is the green line there. So you can see I have that down in y5. Okay, this other stuff is for other problems. But those two are in. If we want to find those intersections, it's the same command, second calculate, and there's an intersection option. Okay, this one's a little different. It's going to ask for different curves. So the first curve is just the blue, the polynomial. Press enter and it will jump to the line 100. Press enter. And now here the guess is kind of important. Since there are multiple intersections, you need to get close to the one you want. Okay, because the method it uses is it's starting out by finding one that your guess is close to. So if we just start with the one on the left, I put my guess somewhere near that, and we will get an answer of about 4.475. Okay, so far we're at 4.475 hours. And now let's go find this one. So from 0 hours to 4.475, we were above 100. Okay, then it kind of dips below for a while, but it comes back at, if we get another intersection point there. So same kind of thing, first curve, second curve, and now your guess just needs to get closer to that intersection point. So that looks pretty close. Enter one more time, and that one was just after 8 hours of being open, so 8.04. And then we'll find one more out here. Okay, so same kind of thing. Another intersection. First curve, enter. Second curve, enter. And just guess, move cursor closer to that point. And then we'll write our final solution here once we get that. So that one's around 11.84. Okay, so it looks like all of the time from technically when it first opened, so including 0 up to 4.475. Okay, those x values, you can see the blue graph is above 100. And then there's another chunk of this stuff, which is from x being 8.04 up to 11.84 hours. Okay, so those are the intervals. Those are the number of hours when the number of customers is above 100. So that's probably the best way to handle that one. Okay, the next two and 3 are more algebraic, okay, less calculator use. You can still do some things on the calculator. So I don't want to be there, I want to be here. So when I say spit method, I want to see the process where you solve it, you plot them, and you do an interval test. So to solve, we're going to pretend like we have an equal 0 in there, and we will get our critical values then. And factoring is probably going to be the best way to do this one. Just it looks fairly straightforward to factor with the minus r and the minus 12. So I'm thinking r plus 3 times r minus 4 equals 0. And that gives me my critical values pretty easily, setting those both equal to 0. Okay, so those are what's going to go and divide our number line. And that'll divide it into 3 intervals then. We have all numbers that are less than -3 in interval 1. We have all numbers that are in between the two in interval 2. And then we have a bunch of numbers that are greater than 4. So we're going to do a little test now and see which intervals would end up working. Okay, so if you're doing this algebraically, you could test and show something like, let's test from interval 1, let's use -4. Okay, and you can test it actually into the factored form. Remember, this was really a less than or equal to 0. So in factored form, if I go into this, if I plug -4 in, that first factor, -4 plus 3 is going to be a negative number. And -4 minus 4 is also going to be a negative number. So that's really going to give me a positive result. And so the question is that result less than or equal to 0? And we got a positive result, so it's not less than or equal to 0. So that one's not going to work. Okay, when you test something in interval 2. A good number to use might be x equals 0. Okay, x equals 0 is in that interval. Okay, if we go into the factored form, or you can go into the original if you want, that's fine. But the factored form is usually a little quicker. If I put 0 in there, so I would get 0 plus 3, which would be a positive. 0 minus 4 would be a negative. That would make the entire thing negative. And that is less than or equal to 0. So interval 2 worked. Okay, you could do the same thing, and just to save a minute here, interval 3 would end up not working again. Okay, and if we need to think about what's happening right at -3 and right at 4, those were when it actually equaled 0, right? So I like to label my interval plot. Okay, because is it okay to equal 0 in this problem? Yeah, based on the original setup here, we're allowed to equal 0. So those endpoints are fine. So -3 would be a closed circle. So would -4, and any number in between in interval 2 would work. So we could write our final solution then in interval notation, just by saying all numbers between -3 and +4 with brackets, not parentheses, because the endpoints are included. Okay. The other option to do the interval test, if you guys like the graphing method, you can do that too. Let's say you graph the original parabola, you would notice it ends up doing something like this. And you can tell just by looking at the graph. Again, think about the original question. It's asking, when is this stuff less than or equal to 0, right? And you can see all the way, these are all the points where the graph is below the line. So the x values that made that work were from -3 to 4. Okay, number 3, similar type problem, but just had one extra little step to it. If we factor the numerator similar manner, x plus 4 times x minus 3, and the bottom is x minus 4. Okay. This one again, if we're going to solve the equation, what you could do is actually multiply both sides by x minus 4. So in this case, if you multiply by x minus 4, the right side's still going to be 0. Okay, and we could solve this the same way and get some critical values of x equals negative 4, x equals 3. Okay, I would go ahead and plot those. Okay, but there's an issue here. If we just set up our intervals, there's also an excluded value in this problem. Okay, so if you recognize from the very beginning, if we plugged in x equals 4, the whole problem would be undefined. So if you're out here testing 4, it's actually going to be an undefined expression. Okay, so you need to put that value on your critical value list as well, and we actually have 4 intervals to test. Okay, so that's really the difference between number 2 and number 3. Number 3 has that as an additional value to check. Okay, and we would do the same thing to kind of test this one out, plugging in, and so I'll do the first couple. If we test something in interval 1, let's say we test negative 5. Okay, that's coming from interval 1. So looking at the factored form, so it's going to be the easiest way to do this without a calculator is looking up here at this form right here. If I plug negative 5 in, so negative 5 plus 4 is a positive number. Negative 5 minus 3 is a negative, and negative 5 minus 4 is a negative. Okay, so that's what my factors would be as far as positive negatives. That makes the top negative and the bottom negative, which makes the entire thing positive. And in this case, that is what we were looking for. Okay, so interval 1 would work here. Now negative 4 itself, the borderline, it actually equaled 0. So let's label that. And in this case, again, equaling 0 is part of our solution. Okay, if x were 3, that's also a 0. So let's do another test point. Let's do something in interval 2. Let's test, again, let's try the number 0, x equals 0. Okay, plugging it in again to the factored form up there. The x plus 4 would be positive, the x minus 3 would be negative, and the bottom would be negative. Okay, so that's going to give me what? A negative up top, a negative on the bottom, make the whole thing positive again. So interval 2 looks like it's working as well. All right, and I'm just realizing there was a little mistake in interval 1. So hopefully as you were watching, you caught that. When we test negative 5, when that went into this piece right here, negative 5 plus 4 would actually be negative right here. So it would actually be a positive over a negative, which would make the whole thing negative. So sorry, so that was actually a no. So I was just making sure you guys are with me there. And then if we do the other ones, let's see what happens there. So if we test something in interval 3, right, we don't have a lot of options. So maybe like using something between 3 and 4, let's use like 3.5. So if I put 3.5 in there, looking at the factored form up there, if I add 4, that's going to be positive. 3.5 minus 3, still positive. 3.5 minus 4, though, would be negative. So this would be a positive over a negative, which would be a negative, so that would be a no-go. Okay, and then we noticed right at 4, the thing was undefined. Past 4, let's say we use 5, we end up with, what was the setup again? X plus 4, so that's positive. X minus 3 would still be positive. X minus 4 in the bottom would still be positive. So this one's going to end up being positive, which is a yes. Okay, so now we're able to put it all together and write our solution. So basically, in this case, again, it could equal 0. So negative 4 was good. That interval worked. Negative 3 was good. Interval 3 was no good. 4 itself was no good. So that's got to be an open circle and to the right. Ooh, I'm out of space here. So final solution in interval notation would look something like from -4 to -3, including the endpoints. And then union, oops, sorry, that was +3. And then from +4 with a parenthesis to infinity. All right, so there's that one. All right, next couple, we'll do these graphs. So again, I would do some factoring, whatever looks factorable, let's try and factor it, get simple form. So the numerator looks like x minus 2 times x plus 1. Okay, and the denominator is a common factor of 2. Take that out first, it's going to make things a lot easier. If you divide everything by 2, we get that. And then the denominator is still factorable a little bit more, so x minus 2 times x plus 1. The bottom has a 2. That should be an x plus 3 times x minus 2. Okay, so we do notice that there is a term that's going to get canceled out here, the x minus 2 factor. So this is really x plus 1 over 2 times x plus 3. All right, so that's kind of our simplest form with everything reduced. And that's where you're going to see your vertical asymptote. Okay, the denominator would be 0 if x were -3. Okay, we also know originally there was an x minus 2 in there that got canceled out. So I know there's going to be a hole if x equals 2. So we got to keep that in mind. Okay, so let's get the other asymptote though first. So we got the vertical asymptote based on the degree. The degrees are the same. Okay, so the horizontal asymptote. Okay, so we just got our vertical asymptote. Let's get the horizontal now. Horizontal deals with the degrees. So since the degrees are the same, I'm going to look at the ratio of the coefficient. So it's really like a 1 over 2. So there should be one at 1/2. There should be a horizontal asymptote. So just kind of carefully put that in at half. 1/2. Okay, we should also be able to get the domain set now. So the domain is going to be all reals except those two things we just found. X could not be vertical asymptote, or x cannot be wherever the hole was. Okay, and then let's figure out what this graph looks like. So you can go in your calculator to kind of figure out where the branches would be. I think I have this one in. Get rid of that other stuff. Don't want to show that one anymore. Don't want to show the 100. So y2 is the one we're doing, right? So let's graph that one in the standard window, zoom 6. And we'll just see what it looks like. So we can see there's the horizontal asymptote at 1/2. We can see the vertical asymptote. And now just remember, there is actually a hole. If I go to x being 2, we said there should be a hole there, right? So there's no y value. So when you draw it, just kind of emphasize that there is a big hole there, because again, this is undefined. So to figure out kind of where it would be, if you needed to know, if you needed the range or something, you could go to this factored form and plug in 2. Let's see where it would be. So if we plugged in 2 to that, so what would we have? 2 plus 1, so 3 up top, over 2 times 2 plus 3, 2 times 5. So it would actually be at 3/10. That'd be the y value where it would have been. So we just kind of need to make sure we account for it. So the graph did something like this, and then something like this. Make sure you emphasize there's a hole there, and then it keeps going. Okay, so just approximates on that. And that's it for number 4. Okay, number 5 then, gonna clear some space here. This one's a little simpler, I think, because there's not as much factoring to really mess with. So this one, just think about looking at your denominator. I know if x equaled 1, we'd have a problem. So that's going to be a vertical asymptote because there's nothing to cancel it out. And then this one I'm going to think of more as it has some shifts in there. Normally the horizontal asymptote in this case, since the denominator's degree is larger, it would normally be at 0, but we do have a shift of +3, so it's now moved up 3. So my horizontal is actually y equals 3 now because of that shift. Okay, and then this one again, you can use your calculator to kind of see where the branches are. I know the negative's kind of going to flip it, so um, if we graph that one, I believe I have that in here too. Yeah, so I'm going to unhighlight y2 and let's show y3 now, just so we can kind of see where it is. So yeah, so this one's kind of in the bottom right now and top left. Okay, and just fit your graph into the asymptotes, and that's about all we can do. So this one kind of goes something like that. That stays up there. So then this for the domain would just be everything except 1. Okay, the last one, word problem setting up a function here. So we have a reunion. It's going to cost $750 to rent the hall, and then $20 per person for their meal. So if we wanted to just represent the total cost, if one person's writing a check, it's just going to be the $750 plus 20 per person, so plus 20x. Okay. So that's just a linear equation. That's just mx plus b. But if we start talking about per person now, I need to take that entire cost and spread it out evenly for each person. So that's a division problem. We're dividing by how many people are there. Okay, so that now is a rational function with an asymptote. Okay, what would the cost be if 100 people attended? That one I didn't calculate out, but you just have to plug in the 100 for both. Okay, so I'll leave that to you guys to check out. All right, so where it really gets good in part 2 here, let's say that we're going to support the 5 oldest members and pay for their meal. Okay, so let's represent a new expression for the cost per person. So basically, the cost is still the same. The total cost is still this. It's just the number of people paying that is decreasing. We now have 5 less people paying. Okay, so instead of dividing by x, where everyone paid for it, we're just dividing by a little bit less. We're dividing by x minus 5. Okay, so that would be the cost per person. So just think again, that total cost, the numerator is divided by x minus 5, right? Because 5 people aren't paying. If we wanted to graph that function, I'm going to show it on Desmos. You guys could use your calculator, set up the window appropriately. It ends up looking something like, let me go to Desmos. It ends up looking something like that. Okay. And we should be able to notice a few things on here. Just by looking at the equation, we should have a vertical asymptote at 5. Okay, which is kind of tough to see, but it would be somewhere around here, right? Now horizontally, we're dealing with looking at the degrees again. So this is a first degree, this is a first degree. So they're both the same. So the ratio there's 20 to 1. So there's actually a horizontal asymptote as well at y equals 20. That's what that thing's leveling off to. That would be the end behavior if it asked about that. Okay, so the last part is now, how much would we need to charge? Let's say we want to keep the cost to no more than $30 per person. So basically what it boils down to is that expression that we graphed. I want that to be less than or equal to $30. Okay. And this is another one, if you want to solve it algebraically, it's really not that bad, but if you want to do it graphically, that'd be fine too. So I'm going to do it graphically where I would graph y equals 30 as well. That's what I had showing here. And use your calculator to find the intersect like we did before. And you'll be able to see right at 90 people. Okay, so if there were 90 people there, that's when the cost would get to $30. And if you have more and more people, you can see that the cost is actually decreasing. It keeps approaching 20, but the cost is always less than 30 for all x greater than or equal to 90. That would be our solution for the last part there. Okay, so that was a good little modeling situation to show this in action. All right.